Live now.
Okay. Now?
Yes.
Okay. Hello, I warmly welcome you to our 13th webinar by the Academy of Space Renaissance International.
Live now.
Okay. Shall I wait? No?
Go.
Okay. My name is Sabine Heinz, and I'm the person responsible for our webinar series. And I warmly welcome you. I don't know if you have listened to it. And I saw in the chat that we have people here watching from Washington, from Poland, from Hawaii. Hello, Jim. And on this 21st of February, I'm delighted that you have come to join us. And our today's topic is cosmic hazards and better planetary defense for Earth and Mars. Our today's special guest is Professor Joseph Pelton. Welcome, Joe. You have to unmute.
Oh, am I muted?
Yes. Yes. Okay. Welcome.
Okay.
And I also welcome Adriano Ortino, one of our vice presidents. And,
hello, everybody. Welcome to this webinar with Professor Joe Pelton that will tell us something very interesting about the protection from cosmic radiation and from asteroids and from other things coming from space.
Okay.
And protection is needed both on Earth and in space.
What I wanted to
going outside. Okay.
Okay. Okay. Before I give you the floor, Joe, I would like to inform the audience about your talk. There's a number of global space-related issues where greater international collaboration is needed. And greater public awareness is required regarding potential threats from asteroids and comets, as well as catastrophic solar storms. ACES worldwide seeks to collaborate with a wide range of space-related organizations, as well as with the United Nations Office of Outer Space Affairs, in order to help to develop better means, policies, and recommended regulations to defend against these threats. Potential hazards include space debris, asteroids, comets, solar storms, and other cosmic threats. I would like to say something about Joe Pelton, our speaker. He is the Director Emeritus of the Space and Advanced Communication Research Institute at George Washington University. He is the founder of the Arthur C. Clarke Foundation, former Dean and Chairman of the Board of the International Space University, and Editor Emeritus of the International Journal of Space Communications. He is Executive Board of the International Association for the Advancement of Space Safety, and he was a founding president of the Society for Satellite Professionals International. He is author of over 300 articles, 50 books, nominated for a Pulitzer Prize and winner of the Literature Prize of American Astronautical Society. He is a member of the International Academy of Astronautics, fellow of the International Association for the Advancement of Space Safety, and associate fellow of the American Institute of Aeronautics and Astronautics. Professor Pelton is also founder and chair of the board of ACES Worldwide, and he is also a vice president of our Space Renaissance International. Joseph, I'm really glad that you are here, and I would like to give you the floor.
Well, thank you. Obviously, I've not been able to keep a job, but I keep trying, and it's been a really interesting period of years. I started out in space applications with ComSat and Intelsat, and then when I became Dean of the International Space University, I became more and more interested in space exploration and other aspects of space. And particularly working with the IAASS, the International Association for the Advancement of Space Safety, where I'm on the executive board. I've become more and more fascinated with the issue of space safety. And as I begin, I'd like to ask everybody who's listening to maybe raise their hand or at least think about it. How many of you have had the chance to travel on a spacecraft out into deep space, billions of miles or kilometers during your lifetime? How many people raised their hand? I don't see that Sabine or Adriano raised their hand, but I would raise my hand because I have been traveling on Spaceship Earth, which is a 6 sextillion-ton spacecraft that travels billions of kilometers and around the sun each year, and traveling at 100,000 kilometers per hour. We go very far around space, which is actually a very hazardous journey. If we imagine Earth, our spacecraft, as the size of an apple, we actually find that the protective shielding of our atmosphere is less than the thin skin of an apple. So we have very little protection. We also have the geomagnetic field that also protects us from very dangerous solar storms and radiation and what's called coronal mass ejections. But we also have to fear the fact that there are lots of asteroids and comets out there that we call potentially hazardous asteroids or near-Earth objects. And all of those things actually threaten life here on Earth. Now, many people would say, if it's so dangerous, if all of that cosmic hazard out there is so dangerous, why don't we have major problems? And what's changed? Has the cosmic problems out there gotten more dangerous? Well, actually, due to solar debris, yes. But the main thing that's changed is not the cosmic hazards, it's life on Earth. That it used to be that there were very few people and they were in largely a rural environment. Up to the 18th century, we were very largely a rural population on planet Earth. But today, we have over 30 cities that are mega cities, over 10 million people. We have over 80 cities that are over 5 million in population, and we have over 500 that are over 1 million. And so we are spreading ourselves more and more over the surface of the Earth, more and more urban and more dangerous. We had an event back in 1908, the Taguska asteroid came down and it destroyed an area of Siberia equivalent to the size of the Bay Area in California, or it could have destroyed any of our mega cities, whether Mexico City or Tokyo, or Paris, Beijing. Just one of these smaller asteroids, which the Taguska asteroid was only about 40 meters in size. And NASA, in its wisdom, together with Congress, has said we're looking for asteroids that are 140 meters in size. And that's not dividing 4 into 140 to get the difference. You have to divide the difference and then cube it. And so that means that the asteroids that NASA is looking for are 60 times larger than the Taguska asteroid, which could be a city killer.
I'm sorry, John, just one thing.
Yes.
sorry. Just tell me, please, when you want to go ahead with the presentation.
Now is the time to start. So,
okay, thank you.
So there are these hazards from outer space, and mainly they come from, next slide, they come from the sun and solar storms, and that is a really major thing that we need to worry about. In fact, it's the most likely thing to happen. And also from asteroids and hazardous rocks that can come from outer space and crash down and destroy our world, as it did for the dinosaurs 75 million years ago. Next slide. So one of the big worries that I'll talk about first comes from the sun. And as you can see, there are all these things that are happening on the sun's surface. There are flares, there's prominences, and there also can be, in addition to the solar wind that's constant, there can be these eruptions that are either flares, which are radiation. And when we have radiation, we need to worry about skin cancer, and we need to worry about mutation, genetic mutation. And actually, if you live near the polar areas, that's a really big worry, because the electromagnetic field is less protective in those areas. And we are seeing toads and frogs with significant genetic mutation problems in these southern regions. And also in terms of skin cancer, if you live, again, near the poles, if you say live in Hobart, New Zealand, or Adelaide, Australia, your chances of getting skin cancer are much, much higher. But in addition to these flares, about half the time when there's a major flare, there's also an eruption of ions. And this is actual mass, and this is what we call a coronal mass ejection. And these can create enormous hazards to our electrical systems and to many of the infrastructure on which our lives depend today in the modern world. So let's look at the next slide. Next slide. So this is a flare, and at the X class and above, these can be very violent, and they can impact our satellites. They can impact launches, as we saw with the SpaceX launch, where there was an unsuccessful launch due to a solar flare recently. Next slide. But the really bad thing is the solar storms. And in 2015, there was this huge long stream of ions burning at 1,000,000 degrees Celsius, and billions of tons of deadly ions flew out, and this one came close to hitting Earth. Back in the 19th century, in 1859, there was what was called the Carrington event. There was a solar astronomer in London who was looking at his reflection. He couldn't look directly at the sun, and seeing the sun with some very, very strange things happening. It looked like a dragon was across the whole large surface of the sun. And he called everybody upstairs to see this very strange phenomenon. And his name was Carrington. And this solar event is named after him, because in 1859, a little over 24 hours later, the eruption of these ions hit Earth, smashed into Earth and our electromagnetic fielding system, and basically crushed it. And the result was that telegraph offices caught on fire. The so-called Northern Lights, the Aurora Borealis, it came all the way down to Cuba and Hawaii. They could see this gigantic flaring in the skies as these bombardments of ions were hitting the Earth's magnetic field and crushing it down and sending the other side of the magnetic field out into space, maybe 50, 60 Earth diameters. And at that time, the only thing that really was electrified was the telegraph system. But today, if that happened today, it would probably destroy our electrical grid system. There was one study done by Lloyd's of London that suggested that if a Carrington event type solar storm were to hit Earth today, it would take something like 2.7 trillion, not billion, $2.7 trillion to restore the electrical grid just for North America. And the bottom line is we are unprepared for that event, because that event might not only take out our electrical grid around the world, it could also destroy the electronics on the pipelines that supply fuel to the world. It could probably take out a large number of our satellites, that the synchronization of the internet, for instance, is controlled by the GPS satellites, and we lost them, we might lose the synchronization and lose internet. The bottom line is such a black swan event we are not prepared for, and very little has been done about it. Due to activities in the UN, there has been efforts to try to do more in terms of asteroid protection, but very little has been done in terms of solar storm protections, even though there is a working group on the long-term sustainability of space that's also been looking at this. Next slide. Now, people will say, well, 1859, that was a long time ago. What's been happening since? Well, in 1989, there was what was called the Montreal event. This took out electrical power from Chicago to Montreal. And here is a picture of a transformer in Chicago before and after. And as you can see, that was not providing very much electricity after this sort of 1/10 of a Carrington event occurred in 1989. In 2003, there was also what was called the Halloween event in Scandinavia, and it also did a great deal of damage. So the point is, these events are happening all the time, and based on historical records, there was something like the Carrington event in the 17th century. There was the Carrington event in the 19th century, and it seems as if something like a Carrington event happens about 150 years apart. And if that's the case, we're overdue for a major strike. Next slide. So this is a representation of what happens with a coronal mass ejection. As you can see, there is a tiny little blue dot that's planet Earth. And what you see in terms of those shapes around Earth, that's the geomagnetic field because we have a iron core, the Earth is like a very big magnet. You can see how the lines representing the geomagnetic fields are tremendously compressed, but being shot out way into space on the other side as this blast of ions hit Earth. And of course, when they hit the toward the center of the Earth, they tend to be pushed away to the polar regions. And we are very fortunate that planet Earth has this electromagnetic shielding. So when we talk about Goldilocks Earth, in terms of being just right, in terms of heating and so on, we're also just right in that we have an electromagnetic shield. It turns out Mars doesn't have such an iron core. It doesn't have an electromagnetic shield. And that is one of the reasons that Mars doesn't have an atmosphere, because it's the solar wind and certainly coronal mass ejections that strip away the atmosphere of Mars. We'll return to that a little bit later. But anyway, these very major electromagnetic storms are from solar storms from the sun are very dangerous to our modern society, because we have more and more people dependent on modern infrastructure around the Earth in more and more places, and more dependent on the internet, on communications, on electricity. The truth is that most people's job in a modern world are dependent upon electricity. And if we were to lose this supply of electricity, there are estimates have been done that it would take 4 to 10 years to restore the electrical grid system if it were to be fried by one of these massive solar storms like the Carrington event. Next slide. So this is a simulation of the Van Allen belts. And of course, they are held in place by the world's geomagnetic field and shaped that way. And that you can see that there are two sort of rings represented by the Van Allen belts. And sometimes there's been actually a third belt that formed and gone away. But if we were to lose our protective shielding, this would be very bad in terms of solar storms. So what is happening in terms of the Earth's geomagnetic field? Next slide. This is the mapping of the Earth's Magnegosphere, and this has been done by the European Agency Swarm satellite, and also that's 3 satellites that are measuring the differences in the magnetic field of Earth as they go around the Earth. And then NASA has a similar system with 4 satellites, and the mapping of the Earth's geomagnetic fields shows that the Earth's poles are in a process of changing, and that, as you can see, the southern pole is moving up toward the tip of Africa and Australia, and the northern pole is moved down to Siberia. That's the orange area you can see up toward the top. And so this means that every so often there is a changing of the poles of the Earth, and the North Pole becomes the South Pole and vice versa. And this hasn't happened for a very long time, but the magnetic field measurements from the NASA satellites, the 4 satellite constellation, and the ESA swarm shows that, in effect, our solar shields are coming down. And blue is a weakening of our field, and red is strengthening. So what does this mean in terms of our future protection against solar storms? Let's look at the next slide. this is some of the modeling that has been done of what would happen to the magnetic poles and our geomagnetic protective system. And between the reversals, as you can see, there's a very strong protective system that's three-dimensional. This is just shown in 2 dimensions. But in the modeling of when our magnetic field becomes the weakest, you can see it's not very good at all, that our protective shielding may go down to 15% of what it is today. So almost all of the factors are coming together to create a perfect storm. Our protective shielding system is coming down. Our population has spread around the world, and that we have got more and more infrastructure, particularly electrical infrastructure, that could be smashed by a major Carrington event type solar storm. Next slide. So what could we do about it? Well, one of the ideas that I've been working on with my colleague, Jim Green, who was until recently the chief scientist of NASA, we've been looking at what I call a Lapse, a Lagrangian protector for solar ejections. And this would be a shield. And when I say a shield, I'm not talking about a actual physical shield, but a electromagnetic grid system that could be placed out at Lagrange point 1, a million miles or 1.5 million kilometers out in space, that could create a protective shielding from Earth from these coronal mass ejections, and also to modulate the radiation flares that come from the sun. And of course, these events happen often, that the sun has a 11-year cycle of solar max to solar minimum, and that during solar max, there can be as many as 15 radiation flares a week, and about half that number of coronal mass ejections. The good news, of course, it goes off in many different directions, and Earth is a small target. But nevertheless, eventually our time is up, and we're going to be hit with a major event like a Carrington event, and we're not prepared for it. And so one of the ideas, of course, is could we create an electromagnetic shield that would protect Earth from these solar storms? Of course, there may be other solutions. There have been proposals about redoing the transformer system and the wiring in electrical power systems to make them much more protective against the major coronal mass ejections. But so far, very little has been done about it. And we really need to give very serious study as we talk about smart cities of making an upgrade of the electrical system to protect them against coronal mass ejections. Next slide. So I think now we're going to change over to worrying about what we could do with regard to Mars. As I mentioned earlier, Mars doesn't have an iron core, and so it has its atmosphere stripped away by the solar wind. But there is a L1 point of Mars that's much closer to Mars, and Mars is a smaller target, and it's much further away from the sun. So a Lapse system for Mars could be much less complicated and less powerful. but certainly 1 to 2 Teslas of a electrical shielding system in studies that have been done by NASA and some of the research centers in the United States suggest that we could create a sufficiently large charge system so that we could create a magnetosphere around Earth, around Mars, to protect it and allow its natural environment to reemerge, that an atmosphere, as we see the melting of water, which is sufficient to create oceans on Mars, could allow the evolution of a perhaps ultimately a breathable atmosphere on Mars if we just were able to create a large enough electromagnetic shield for Mars. So the major problem in looking at this is the problem of tailing, of that if the shielding system is not powerful enough, then the wave of ions would then tail around that shield and come back and then smash into Mars. But we feel that with maybe 2 Teslas of electrical magnetic charge, we could protect protect Mars from this type of event. And so this is an area where I have been working on for a number of years, and working with groups like the Lifeboat Society and others to see whether we could bring this idea forward so that all of the space agencies of the world might be able to work on this kind of a concept for Mars and for Earth. And this is, in my view, a much needed investment, and could be one of the most eventful things we could do in space. Next slide. I think now we're turning our attention to asteroids. Asteroids are a danger, and here's one that swept by Earth in 2014. It was detected only 3 days before it went by, and it had a kinetic energy of a nuclear bomb. And again, as I noted, a 35-meter asteroid is enough to be a city killer for a megacity, and that we have the experience just a little over a century ago of a hit that could have wiped out any one of our megacities if it were to hit Earth. Next slide. So what could we do about this, and what are we doing about it? Well, first of all, there is an annual appropriation for NASA, and for planetary defense activities, it adds up to $150 million out of well over a $20 billion budget. And again, Congress has set the parameters for what we're looking for in terms of potentially hazardous asteroids at 140 meters. But that is 60 times larger than the Tunguska strike. And clearly, we should be spending more money on planetary defense, and clearly we should be looking for larger, for many more asteroids of the smaller size of the Tunguska strike size. In other words, we should be looking for asteroids that are 60 times smaller than what we're currently looking for. NASA has done some good things. There was the so-called NEO-WISE project, which took the WISE infrared telescope and repurposed it to looking for asteroids. But again, it was geared for these much larger sized asteroids. There was a proposed project called the Sentinel Infrared Telescope Project, which was developed by the so-called B612 Foundation. This was headed by my good friend Rusty Schweikert, the Apollo 9 astronaut, and subsequently by Ed Lu, another astronaut. And their idea was to build a infrared telescope that could detect much smaller asteroids and be much better able to detect comets, centaurs, and asteroids. A centaur, incidentally, is a comet that's caught by the fields of, say, Jupiter or Saturn, and then escapes and comes toward Earth, or at least we hope not toward Earth. Next slide. So this was the canceled Sentinel satellite and infrared telescope that the B612 Foundation tried to raise the funds to do it, and NASA decided not to fund it, even though, in my view, it was a much better design program than what NASA is planning currently for their surveys of potentially hazardous asteroids, which are a much bigger problem than, again, the general public appreciates in terms of the damage it could do. When people think about the Earth, they really don't understand that every year there is 5,000 tons of so-called stardust that comes down to Earth. And this includes a lot of meteoroids and sometimes bolides that come all over the world, and that we really are a potential target for all of these millions of meteoroids and bolides, and certainly good-sized asteroids that are still out there. Next slide. So this is just a representation of looking across the solar system of all of the millions of asteroids that are out there. They do tend to be in the same plane as the solar system as we know it. And this just gives you some idea of the tremendous numbers of asteroids that are out there. And of course, the smaller they are, the more there are of them. Next slide. And just a final word about the issue of space debris. When the issue of space debris was first brought up by colleague Donald Kessler, there was very little debris out there, but there is a picture that I have that shows the buildup of debris year after year. And as you can see, there are now 22,000 elements being tracked. And of that, there is some 10,000 tons of debris in Earth orbit, and 45% of that is concentrated in the low Earth orbit, as shown here. And with the new space fence, with the S-band radars, we're now going to be able to track over 100,000 elements. And this means down to the size of a marble. Now you might say, well, a piece of debris the size of a marble, that can't do too much damage. But if this marble is moving at 17,000 miles per hour or 25,000 kilometers per hour, even that has the explosive force of a grenade. And so we really have a serious problem with debris buildup, and with the launch of so-called mega constellations like SpaceX, its system, two systems involve some 12,500 new satellites. China has actually filed with the International Telecommunications Union for a system that involves 13,500 satellites. And we really do not have a good system for deorbiting satellites. There have been studies done by Aerospace Corporation simulating the 5 largest of these new mega constellations. And in each case, they found that either during deployment or deorbit, there was a very significant chance of more than one of the more than one chance of a collision, and each collision typically results in 2,000 or more new debris elements. Next slide. So what are the conclusions? First of all, space hazards are real and can lead to truly black swan events. The global capabilities to detect these hazards and defend against solar storms, as well as potentially hazard asteroids, comets, and centaurs, and even space debris, are totally inadequate. The space community has an obligation to get the world's political leadership to recognize these dangers and to create programs to defend humanity from cosmic hazards. All space agencies should create a unified global program for planetary defense. Next slide. So the Alliance for Collaboration in the Exploration of Space, which we just called ACES Worldwide, is working with a network of organizations to raise global concerns about cosmic threats from solar storms, asteroids, centaurs, and comets, and orbital space debris. And we are urging the creation of a new global agreement that recognizes these threats, sets forth an action agenda to address more clearly the nature of these threats, new ways to address these threats, and to emphasize the need to undertake mitigation strategies in all these areas. My pet project, of course, is to create electromagnetic shields at L1 points for Earth and for Mars. This, as noted, will not only help protect Earth from a black swan event, if a Carrington event were to occur again, but also could allow us to create over time a breathable atmosphere for Mars and for the future of what many of us at the Space Renaissance International are hoping can happen in future years. Next slide. That's it. Okay, do we have time for some questions?
Okay, thank you so much for this interesting lecture. I also would like to welcome our president, Bernard Foying, and I would like to give you shortly the word before I take the questions from the chat. You have to unmute. You have to unmute. Yeah.
Yes, I have the pleasure to talk to you from America. So I've joined our colleagues from Space Renaissance International US chapter as we had an event. We organized a launch event from Wallops Island where we sent the first art science gallery into space. It's now being docked on the International Space Station. It arrived this morning very early. We even had the chance overnight to watch the International Space Station from this very terrace here, this is a head office of the International Moon-Based Alliance on the 43rd floor of a building in New York. I am here with Hank Rogers, one Space Renaissance international members. And so it's great to see also the talk from Joe Pelton that brings me back to my youth, where I was doing a Ph.D. actually on solar flares and solar corona. And now we have tried to develop over years an initiative of space weather, space debris protection, planetary defense. And it took quite a lot of time to get some support because eventually the taxpayers or the politicians didn't realize that it was for our own protection, and it was not only for scientists that we are doing that. And more recently, so the European Space Agency has created a new program they call Space Safety that includes all those aspects together: space weather, planetary defense, space debris, but also traffic management. And then this way it has a sufficient mass so that people take seriously the effort. And now we have learned that it's very important to listen to the scientists, but also like, for instance, what happened to the Starlink constellation could have been avoided by just having, some of our top experts that know that there was a magnetic storm and that the Earth's atmosphere inflates and that increase the drags. And I heard from the SpaceX team now that are we going to launch a bit higher than these 200 kilometers starting altitude. So it's very important that we play our role to connect the scientists, what we have learned from them, but also to practical problems of space, space application and space exploration. So I wanted also then to ask Joe Pelton a question. So how do you see that this initiative on space safety that European Space Agency has started could be managed on the world level? That's the first question. And the other, how do you see, this shield that you propose around Mars, what is the roadmap to create this shield and to eventually make Mars a bit more habitable than it is now?
Right. Well, of course, the first issue would be appropriations to actually get this started. In other words, to get the space agencies of the world to agree that there should be a unified project on space safety. And the point is, right now, they're all split up. In other words, there are some people who are working on solar flares, some people who are working on coronal mass ejections, other people who are working on asteroids. If you put all of the areas related to planetary defense together in each of the space agencies, this could be a very sizable program. And we've done things like the International Space Station, where we have put together a global alliance to work together on a major initiative. And certainly the Space Shield would be an excellent example of something that you could do as a joint project in terms of funding it and managing it. But also, again, a project such as the Sentinel project that the B612, that again could be funded and supported by alliance of space agencies and so on. But the point is, these are not things that the US should worry about, or Europe should worry about, or Asia should worry about. The world should be worried about these issues and recognizing, hey, if we work together as a team, we could do a much better job of defending Earth and making the money count, because there's all of these projects that, if you will, are sorry, I was just hanging up a call. Anyway, I do think that these are things that we can work together. Hi, Hank, how are you?
Hey, all right.
And clearly, so you're talking about the scientific rationale, the technical feasibility, but also learning to work together to address global challenges. So I have with me Hank Rogers. So not only is a founder of International Moon-Based Alliance, but on the topic of climate change, is trying to be very active. So that's a model we could follow also for some of the action you propose. So Hank, what do you think about
before we ask the question, I actually have a book out which is called Space Systems and Sustainability. And 3 of the chapters are on cosmic hazards, but the other chapters address climate change, global pollution, pandemics, and so on. And the whole idea is to create a sustainability treaty where all the nations of the world would agree, here are planetary threats that we need to address as a team, and to create a process first to identify what those major threats are, and then secondly, create a framework for funding and actually working on planetary defense as a global team, rather than everybody having their national program to work on what are truly global threats. To me, it's very logical.
Yeah, it's very logical. And I've been to several COPs now, COP 24, COP 25, COP 26. And the lesson that I learned is that a bunch of countries can't get together and decide anything. There's just too many cooks in the room with too many different issues. And so basically the way I'm biting off climate change is I'm saying, look, forget about trying to fix the entire world, fix your part of the world. And kind of did it in Hawaii. We have Hawaii has a mandate. We were the first state in the country to have a mandate for 100% renewable energy. And we followed it up by changing the business model of the utility. So they actually make more money the quicker they switch to renewables. Guess who's our best friend now? So I started a new nonprofit in New York, and we're doing the same thing with, first of all, island countries. And then we go from because they're the easiest, they're the ones who are hurting the most, who are spending the most on fossil fuel, and they stand to gain the most by switching to renewables. So we're going to go island hopping first, and then we go to countries and bigger until the whole world has a mandate of 100% renewable energy by 2045. And that date came to us in a negotiation with the politicians in Hawaii. But actually, it's a really good date because it's the 100th anniversary of the United Nations.
Oh, okay.
What better time to fix everything
Okay.
but the 100th anniversary of the United Nations? So that's my target. That's why I'm in New York. I'm sorry, I'm cheating on the space industry by working on sustainability, but we got to do what we got to do. We all do.
Thank you very much, Hank. So back to you, Sabina.
Thank you. I think this problem with the space debris can be solved only on an international basis. And I think maybe with some insurances that everyone who puts some satellite in space has to pay some insurance, that it can be recollected when it is done. I will go to the chat now and we have here from Lucid, she said also that global space programs, the sooner the better, and is asking where does the Van Allen belt go in the case of magnetic shift? Does it come down to Earth?
Well, I agree. I'm not sure what I can add, but I think that is clearly we need more global cooperation, and it's very hard. I think Hank makes a good point of think globally but act locally, that start things at home. But we do need more global frameworks that can actually work, and that, you know, specific projects, whether we're talking about a space shield or other projects like what I would call a Sentinel 2 project that we could and should fund globally. My first job when I was an intern at NASA was in the International Affairs Unit. And there was a man named Arnold Frutkin, and he said, let's not trade money, but let's put together projects where people can do things that they can do together. And that turned out to be a very good formula for NASA's international affairs cooperations. So sometimes it isn't a matter of pooling money, but pooling resources to do things. And ESA and NASA has shown that time and time again can work.
Yes. Can we go to the questions? Where does the...
May I have a couple of questions too?
Yes, but I would like to put the question from the chat. I think the question was not answered. Where does the Van Allen belt go in the case of a magnetic shift? Does it come down to Earth?
Well, the thing is, when you have a coronal mass ejection, there are quintillion of ions, many tons of ions that come as a blast. And when they hit the Earth's magnetic shield, they tend to splay off toward the polar regions. But the stronger the blast, the more can come through to actually reach Earth and reach the pipelines, reach the grids, and so on. And so a Carrington-style event that does reach Earth, and that can burn up electrical transformers, that can burn out the controls on pipelines, and it also can even impact the automatic control systems that control elevators, that can also, if you lose power, you lose communications, you lose the internet, and so on. So the truth is, we are not prepared for a Carrington event if it hit today, because we could lose electrical power, we could lose the internet, we could lose telecommunications, we could lose satellites. We don't really know what the impact would be, but it would be very, very bad, and we're very, very unprepared.
The next question is, how would the Lapse shield deal with the momentum imparted by what it blocks?
Could you repeat?
How would the Lapse shield deal with the momentum imparted by what it blocks?
Well, the thing is, the electrical magnetic shield, if it's powerful enough, will divert the flow. And so the ions will continue, but they would go around the sheath, and they would be pushed off enough to go past Earth or to go past Mars and not impact Earth or not impact Mars. But you need a very large electromagnetic force to do this. And we definitely would need to be doing experiments with much smaller types of to do it at very small scale, the 1,000 scale, to try to figure out what can really be. The main problem is the tailing issue of if your shield is far enough out, can you create enough diversion so that it would go around Earth or go around Mars and not come back and hit our respective planets?
And the last question from Andre, have you studied other orbital configurations, configurations for IR Sentinel telescope?
Well, you know, almost all of the telescopes for detecting asteroids or what have you are infrared. And the idea is that even though these rocks are cold, they still are much warmer than space. And so you can detect asteroids by the infrared telescopes. And we've had the NEOCAM, the NEO-WISE, the NASA NEOCAM is a nice project. But again, it's geared to the wrong dimensions. It's for detecting asteroids that are bigger than 140 meters when we should be detecting much smaller asteroids. And that's why I like the Sentinel design as a much better approach.
Mm-hmm. Adriano has also a question.
Yes, thank you. So first of all, a consideration that, of course, it is very important to develop strategies of protection from cosmic radiation and other things that come from space, because we are in danger even on Earth, not only in space. And of course, the same technologies, or a little bit different, but however, the same concept will be useful to go in space when we will settle the geolunar space region and Mars and etc. And by the way, it's always worth to recall that the real solution to our Earth problems, the climate change and the pollution and everything, is to start expanding, to start civilian space development. Therefore, it is very important, this call to collaboration, to international collaboration that Joe Pelton and his group ACES Worldwide is doing, because these studies for the technologies to protect life in the cosmos, because Earth is in the cosmos, it's not somewhere else. So protecting life in the cosmos is our priority if we want to continue our civilization. My technical question is this one. I'm not okay. I'm not a scientist, so it's not easy for me to understand. But when you talk about a shield, are you're not thinking about a physical shield? I mean, a solid material. You're talking about maybe some generators of magnetic field that stay in a Lagrangian point, for instance, and generate a shield all around, only in the direction of the sun, because it is not needed. The same shield is not needed in the direction of the planet you want to protect, right? So I don't claim to understand the scientific concept. However, I would like to have a few sentences explained to a child of 6 years, okay, how it could work in few words, in simple words.
So first of all, you're right, it's not a physical shield, but you will have to have some physical apparatus to generate this very large electromagnetic field. And there are various things about maybe inflatable structures that we could put a really large charge. 1 or 2 Tesla may not sound a lot, but that actually is a very large charge, because actually you can go down to billionths of a Tesla. But the thing is, we don't really know how to best do this. There are a team of people, about 20 people, some at NASA, some at other of the major research institutes, who've been looking at this concept and what could be done. But first step would be to do experiments with very small scale systems to try to get a idea of how the shielding would work, what the tailing characteristics would be, because that seems to be the #1 issue of that. You know, 1 million miles out is the stable point where the Earth's atmosphere, Earth's gravitational field and the sun's cancel out. So this is a very stable location to put it, but that's also very far out. And so the idea is, can you create that shield at that distance away from Earth, powerful enough so that it will go past Earth and not hit the Earth on either side? And so we need experiments to try to see if we can create a design concept that can work.
I think the main problem would be to collect enough power, enough electric power from the sun.
Right,
so
because it's electromagnetic field.
Have a large panels to get the solar power and large panels to generate the field. So it's, yeah.
That's exactly right. How do you get enough power to generate enough electromagnetic shielding to make it work? And so it's a real challenge, but I think it could be done for less than the cost of the International Space Station.
Yeah. So the last question, the last stupid question. Do we already know how to generate a magnetic field? Do we know how to do it?
Oh, yes. But the point is, can we get one that's large enough?
Okay, fine. So we know how, but we have to experiment the large size that is needed. Yeah, thank you.
Absolutely.
Bernard?
Thank you all very much. I hope it was of some interest and a little bit different than the normal presentation, but it's something that I care about very much. And with regard to ACES worldwide, we are planning to have a panel discussion on this. This will be chaired by my friend Sergio Camacho Lara, who used to be head of the UN Office of Outer Space Affairs, but he also worked with astronaut Rusty Schweikert and other people to get the United Nations to agree to create this International Astro Warning Network, as well as the Space Mission Planning Group, to basically say, if we know of a threat, what can we as a nation, a group of nations agree to do to divert that asteroid from hitting Earth. So those are two very major accomplishments in terms of a global cooperation with regard to asteroids. We need similar action with regard to solar storms.
Bernard, you wanted to say something before I close?
Yeah, okay, thanks very much. Yes, I was reflecting about this issue of this shield, because clearly the size and the energy is for this, you really need to go step by step to really determine if it's just an idea on paper and how you could get such a huge infrastructure to produce it, and is it really worthwhile? One possibility would be to do some tests in smaller scale, like for instance, on the surface of the moon. There are also some areas which are some magnetic shield, very local, and we could try to see if we could bring some artificial magnetic shield, of the size of habitat, for instance. But on the size of the planet, that would be something that would be billions of times more than just. So I don't see that when you say the cost of the International Space Station, I've not seen yet a convincing estimate. So let's pursue the idea, but we have to be careful not to sell it before we have demonstrated its feasibility from the theoretical point of view, but also from the technical point of view and on the implementation side. And clearly, we have to go learning, and eventually the moon is a good place to test some of these ideas at a small scale.
Well, I agree with you. We do need small scale experiments, and maybe the moon is a very interesting idea. So, but
Yeah.
I think even much smaller than that to get started.
Yeah.
Here's a comment in the chat regarding this. Lucy is saying converting in a solar system asteroids into space structures might be the answer, and it would also be help the advent on into development of asteroid mining.
Yeah.
Global test bench.
Yes, and one point, a good shield is to go in a lava tube. Then
Yeah.
the nature has already done the shield for you. But yes, we have to also to find some new solution. Yeah.
I thank you so much, Joseph, for your lecture, for being here with us. I thank you, thank Bernard and Adriano, and of course our audience. And I would not like to close the webinar without pointing your attention to, or invite you to our next webinar. Our next webinar will be on the 7th of March, and we will celebrate the International Women's Day. I will talk with Seth Shostak from SETI Institute about women in astronomy. So it will be a very nice lecture, I think. And I also would like to ask you to subscribe our video channel, our YouTube channel, and to become a member of SRI. We are a non-profit organization, and we also are happy if you would donate something, because we are doing this on a volunteer basis. And yeah, thank you for joining us, and I hope to see you again on the 7th of March at the same time. Thank you. Bye.
Bye. Ad Astra.
Ad Astra.